Today we are going to put our knowledge of potential energy and kinetic energy together to develop a clear understanding of conservation of energy. Let's start off by looking at this simulation. We have a bulldog on a ramp. He's a certain height above the ground, which means he has potential energy in the form of gravitational. Let's push play and see what happens. So you can see that the bulldog starts at a certain height and he ends up going back up to the same original height that he started at. That means the energy that he has initially is the same energy he has at the end. Let's add a bar graph and see how the energy transforms within his path as he goes down. So at the top, you can see he has only potential energy. All of his energy is in the form of gravitational potential. And as let's slow it down a little bit. As he goes down the ramp, at the bottom of the ramp, he has only kinetic energy. He has a little potential because he's a little bit above the ground here. But both of these bars, the green and the blue, add to our total. Let's continue playing and see how much energy he has halfway up the ramp. A little bit more than halfway up the ramp, he has a little bit more potential energy than he has kinetic. But the sum of both of those never exceeds the grand total. So we can see that the energy may be changing between potential and kinetic, but he's never losing energy and he's never gaining more energy than what he started with. However, if we decided to add some friction into our track, now we're introducing another type of energy, thermal energy. So we can see that the bulldog doesn't go as high as he did before. And as he continues, we're converting more and more of our potential and kinetic energy into thermal energy, our red bar on the bar graph. But our total, the red, the blue, and the green, all of our three energy types added together, always equals our total energy. So no matter what, we may be transforming our energy types from one form to another, but we are never gaining energy overall and we're never losing energy overall. It can be changed from one form to another, or it can be transformed from one object to another. So let's summarize what we just talked about. Conservation of mechanical energy. Mechanical energy is kinetic energy plus potential energy, either in the form of elastic or gravitational, or both. If all forces are conservative forces, like gravity and springs, mechanical energy is conserved. Last thing we should note is that energy cannot be created or destroyed, only conserved. Let's think about a discussion question related to this. If we have a dart placed into a dart gun, which is compressed by a spring, what types of energy does the dart have before it is fired, right here, and after it is fired, right here? Let's pause the video and think about it before we come to the answer. Okay, now that you've had a chance to think about it, well, before the dart is fired, it has potential energy due to a spring. So, it has potential energy elastic. After it's fired, it's actually moving out of the gun. So it has kinetic energy, which is energy of motion. I want to introduce this analogy of our energy bucket. Our energy bucket always has to stay full no matter what. So at the beginning, before it's fired, the dart has complete potential energy, elastic. And after it's fired, it has complete kinetic energy because it's moving. But no matter what, our energy bucket must stay full. So let's take a look at an example problem. How fast is a 0.01 kilogram dart moving when it leaves the gun if the spring constant is 100 Newton over meters and it is initially compressed 8 centimeters? Well, we always want to start with energy initial is going to equal our energy final. We have potential energy initial, so potential energy specifically elastic potential energy. And at the end, we have kinetic energy. Well, our equations for both of these are as follows. 1/2 kx squared equals 1/2 mv squared. We can see that our 1/2s cancel on each side, and we can divide over m on both sides. The one on the right hand side will cancel, leaving us with v squared equals kx squared over m. Well, we want the square root of this because we only want one v, so let's take the square root of both sides. We get velocity equals the square root of kx squared over m. Now if we plug in our values, let's clear the screen a little bit. Okay, if we go ahead and plug in our values, we get the square root of, our k value is 100 Newton over meters. Our x value is how much it's compressed, which is 8 centimeters, so that's 0.08. meters, and we want to square this value divided by the mass, and our mass is 0.01 kilograms. When we plug this into our calculator, we should get, and make sure you verify this as well, 8 meters per second as our velocity. Okay, for our second discussion question, a glass is at rest in a person's hand. The glass is then released and falls toward the ground. What type of energy does the glass have right when it's released, just before landing, and also halfway down? Let's pause the video and think about that first. Okay, right when the glass is released, it has gravitational potential energy because it's a certain height above the ground. And just before it lands, it has kinetic energy because the glass is moving. It has no potential energy right before it hits the ground because it's right above the ground. So we're going to say the height is a little bit above zero, but it's so close to zero that the potential energy we're going to consider to be zero. And halfway down, it has half potential energy and half kinetic. So once again, you can see that our energy bucket is remaining full at all times. Okay, here's another example. A glass with a mass of 0.025 kilograms is dropped and hits the floor with a speed of 5 meters per second. What was the height of the glass's center of mass when it was dropped? Okay, for this problem, we're going to need to start with our energy initial. Which is going to equal our energy final. And the type of energy we have initially is potential energy gravitational is going to equal kinetic energy. So mgh equals 1/2 mv squared. Well, you can see that our masses really didn't matter because mass cancels on both sides of the equation. And we're looking for h, so to solve for h, we want to divide g over onto both sides, so our equation becomes h equals v squared in the numerator divided by 2g. Let's plug in our givens. Has initial speed of 5 meters per second, and we're squaring that, divided by 2 times 9.8, it's our acceleration due to gravity, meters over second squared. when we solve for this, we should get a height of 1.27 meters. All right, for discussion question 3, a marble starts at point A against a compressed spring. When the spring is released, the marble rolls along the track until it reaches its maximum height at point C. What types of energy does the marble have at points A, B, and C on the track? Let's pause the video and think about that first. Okay, well at point A, the marble right here is compressed to the spring, so that must mean it has stored energy, potential energy elastic. When the marble is rolling, it's not connected to a spring and it's not at a certain height, but it is moving, so it has kinetic energy. And at point C, when it gets to the max height, it's not connected to a spring, so there's no elastic potential energy. It barely reaches the max height, which means that at its max height, it's not moving, so it has zero kinetic energy. And it is a certain height above the ground, so it has gravitational potential energy. Okay, for discussion question 4, we're going to involve some numbers this time. So our spring constant is 250 Newton over meters, and the spring is compressed a distance of 0.05 meters. It's released and it reaches point C, its max height. What is the height if the marble has a mass of 0.02 kilograms? The challenge question to follow that is going to be a new spring placed in this same scenario, but we don't know its spring constant. We know that it's compressed the same distance of 0.05 meters. And we know this time it reaches a max height of 2.9 meters. What is the spring constant K of the new spring? Go ahead and pause the video and try discussion question 4 on your own first, and then continue watching for the solution. Okay, if we want to know the max height that the marble's going to reach, we need to talk about its initial and its final positions. Well, our initial is going to be right here when it's connected to the spring, and our final is going to be over here when it reaches its max height. So the initial energy that it has is only spring potential energy, and the final energy that the marble has is only potential energy gravitational. Well, when we plug our equations in, 1/2 kx squared equals mgh. And we are solving for height, so let's get height by itself. We get kx squared in the numerator and a 2mg in the denominator. We can plug in our values. Our mass is 0.2 kilograms, and gravity is always 9.8 meters per second squared. When we solve for this, we should get a height of 1.59 meters. Make sure that you plug these numbers into your calculator and that you are verifying this as well. Okay, now we're going to do the challenge question. This time we're replacing the old spring with a new spring. So we don't know its spring constant, but we do know the max height. So let's set our energy equation up similar to last one. Energy initial equals energy final. We know initially that the marble has spring potential energy, 1/2 kx squared, and we know finally that the marble has potential energy gravitational, so mgh. We are looking for K. So let's get K by itself. We want to multiply 2 on both sides. This one cancels. And we want to divide by x squared on both sides. We're left with K is equal to K is equal to mgh, 2 in front, 2 mgh over x squared. When we plug in our values, we get 2 times our mass is 0.2 kilograms times gravity, 9.8 meters per second squared, times our height of 2.9 meters, all divided by how far our spring is compressed initially. And it's compressed the same amount as last time, 0.05 meters. Let's square this value since x is squared in our equation. When you solve for k, we get a higher spring constant than before, 454 Newton over meters. And this makes sense conceptually, or it should, because if we have a spring with a higher spring constant, that means it's stiffer. It's going to have a larger potential energy stored up, which means if we start with initially a larger potential energy here, by the time that marble gets up here, it's going to go a higher height, which it does. It goes 2.9 meters, as opposed to the last problem where we only went 1.59 meters. Okay, for example 3, we're going to do a problem with Tarzan. So Tarzan drops from a 20-meter high branch in a tree, holding on to a 30-meter long vine, which is connected to a second tree. First thing we want to do is draw a picture, and then we're going to find a series of unknowns. Let's do A first. Okay, so our picture, bear with me on my drawing. We have a tree. With a branch that is 20 meters high. And here's Tarzan. Okay, holding onto a rope, which is connected to another branch. The only thing we know about the rope is that it is, or a vine, is that it's 30 meters long. Okay, so it's connected to another branch. And Tarzan is going to swing. Let's see, let's change color. Tarzan is going to swing on the rope. And we're looking for a series of things. We're looking next for, if he barely skims the ground at the bottom of the swing, how fast will he be traveling at the bottom? So we're looking right here. If Tarzan is on, actually it'd be more, we look at our vine. I guess my picture should have been a little bit drawn over there a little bit more, but let's see, if our vine's right here, Tarzan would be right there. So let's think about what kind of energy Tarzan has at each of these points. Well, initially, Tarzan is a certain height above the ground, not moving, so he has potential energy gravitational. At the bottom, right when he barely skims the bottom of the ground, that means he's not a height above the ground at all, he has zero potential energy, and he's moving, so he has only kinetic energy. We're looking for this velocity. So let's set up an equation. Okay, energy initial is going to equal energy final. And the energy he has initially is potential energy gravitational converted to kinetic energy. So mgh equals 1/2 mv squared. We can see the mass of Tarzan didn't even matter because it canceled out. We're looking for velocity, so if we solve for v, we get the square root of 2gh. When we plug in our givens, 2 times 9.8 times our initial height, which was 20 meters, we get a velocity of 19.8 meters per second. Okay, for part C, we are looking for what his max height is going to be that he will swing up on the other side. Well, our initial and final are going to change a little bit. Our initial is still the same. He has potential energy gravitational. But if we're looking for the max height that he swings up to, we know that at his max height, he's not moving, so he only has potential energy gravitational. So when we set up our equation, energy initial equals energy final. We're going from potential energy gravitational again to another potential energy gravitational. So mgh equals mg, let's call this h max because that's its max height. Well, we're looking for h max, so h max equals, we can see that m's cancel on both sides, gravity cancels on both sides, so h max is going to equal our h initial, which was 20 meters. So his max height that he goes up to is 20 meters again. Okay, for part D, we're going to repeat part B and C, which was finding the velocity as he barely skims the ground, and C, the max height, assuming this time he pushes off with a velocity of 10 meters per second. So this changes things a little bit. We can see that now he not only has potential energy gravitational initially, but since he has an initial velocity, he also has kinetic energy. Okay, that's the only thing that changes. Okay, let's solve for this so we can see that energy initial equals energy final. The energy initial is this time potential energy gravitational plus kinetic energy equals solely, we have to do part B before we can do part C, solely kinetic energy. Okay, so mgh equal plus plus 1/2 mv squared is going to equal 1/2 mv squared. This time we're looking for velocity at the bottom of this path. So if we take a look at our equation, we can see that m's cancel out of all of these terms. And if we multiplied through, I'm not a huge fan of fractions, and it makes solving a lot easier if we get rid of them. So if we multiply through the whole equation by 2, so 2 on this side of the equation, and multiply through another 2 on this side of the equation, we can see that this 2 cancels with a half here. This 2 is going to be multiplied by mgh and a half, so this one's going to cancel. When we rewrite our equation, it becomes (2gh) plus v squared, and this is an initial velocity, so let's specify, equals v final squared. We're looking for v final, so let's take the square root of both sides of our equation. So v final is going to be equal to the square root of 2gh plus v initial squared. When we plug in our givens, we get 2 times 9.8 times our height, which was 20 meters, plus our initial velocity, which is 10 meters per second. We want to square that. When we solve for VF, we get a velocity of 22.1. meters per second. And this is faster than he was moving last time. And it makes sense. He should initial velocity as opposed to last time he didn't have an initial velocity. Let's continue and let's solve for that max height as well. So this time when we're resolving for C, the max height, our energy initial and our energy final change again. So Tarzan has potential energy gravitational and kinetic initially, and after he only has potential energy gravitational. This is our max height we're looking for. So when we solve, we get mgh max our h max is what we're looking for. So our m's, we can see, cancels out of all of our terms. And we solve for h max. That means let's go ahead and divide through by gravity. This gravity term is going to cancel out of this term, but not out of this one. So let's rewrite that. H max equals H initial plus V initial squared. We have a 2 left in our denominator, and gravity. When we plug in, we get 20 meters plus our velocity initial is 10 meters per second. We want to square that value, divided by 2 times 9.8 0.8 meters per second squared. When you solve for H max, you should get 25.1 meters. And this makes sense. Last time he only went to a max height of 20 meters, but this time he's able to go higher than his initial height because he had kinetic energy in addition to potential energy gravitational. For the final part, we're looking for the angle that the vine makes with the vertical. Here's Tarzan, 20 meters up on a branch. And we know that he's hanging from a vine that is 30 meters long. So if we went ahead and drew this, we can see that this is 20 meters up. So if the vine is 30 meters long, when he goes ahead and holds onto the vine and falls down, we can see that this is also a total height of 30. So 30 minus 20 gives us 10 meters here, and this is a right angle. So we can use our knowledge of trigonometry to find this angle with the vertical right here, theta. Well, we have the adjacent side length, 10, and we have the hypotenuse, 30. So cosine of theta is going to equal adjacent over hypotenuse, 10 meters over 30 meters. When we solve for theta, we get inverse cosine of 10 over 30. Solve for theta using a calculator, we get an angle of 70.5 degrees with the vertical. Okay, so the next thing, you're going to see a video clip of Wile E. Coyote pushing a bowling ball down to hit the Roadrunner. I want you to think about what is wrong with this video clip. How does it defy physics? And write it down in the box as you're watching the video.
Meep, 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 meep. Meep.
A final discussion question I want you to discuss with a partner is if we had a bowling ball attached to a wire to our ceiling and it's released 1 inch away from someone's face. It then swings across the room and then back towards the person. Which of the following is true? It will A, gain speed on the way back and hit the person in the face, B, stop 1 inch from the person's face, or C, lose speed and not make it all the way to the person's face. At this point in the lesson, you should be able to answer this question correctly. Make sure you discuss the answer with your neighbor and why you chose the answer.